Hello, we will talk about an important lesson and application of sectoral structures theory today. Sorry, I don't have my microphone, so I will speak loudly. Today we will talk about the conjugate of a sectoral structure, and we will find an interesting correlation with some of these conjugate sets. So let's begin by quickly defining what we mean by a conjugate. Let's go back to the basics. For a beta joint and an alpha joint, we will use this bar symbol to indicate a conjugate, and we will say that the conjugate of a beta joint is an alpha joint, and the conjugate of an alpha joint is a beta joint. So that's pretty easy to grasp. Now, when we talk about a sectoral structure, let's look at this example. AN equals to 212 subscript 5. And this is what it looks like when we draw it out geometrically. Now, we will identify the joints of this sectoral structure. We start with the delta joint here. We have an alpha, a beta, and an alpha. Now, if we want to consider the delta joints, then the conjugate of a delta is still a delta. But we are not gonna go into that. So here we have alpha, beta, beta, alpha. When we take the conjugate of this structure, we change the alpha to a beta, we change the two betas to alphas, and we change this alpha to a beta. So we end with a new sectoral structure, and that will be equal to AN bar is equal to 131 subscript 5. So we will say that these two sectoral structures are conjugates of each other. Now, of course, notice that the conjugate of a given sectoral structure of degree n will still have degree n, so it will still be part of the same complete sectoral set. Now, in this case, we have the same order for both, but it does not have to be the case. In fact, most of the time it won't be the case. And of course, notice that the conjugate of the conjugate gives you back the initial structure. So if we can indicate two bars, it gives you AN one more time. Now, if we have two isomorphic or congruent sectoral structures, AN and BM, their conjugates don't have to be isomorphic. So that's a very important thing to note. And here we start seeing why isomorphic sectoral structures, we don't really treat them like equivalent sectoral structures. Because many times, when we apply different functions to them, we will get different results. So they're really two different geometric entities, but they have this isomorphism. So the conjugates of two isomorphic sectoral structures are not isomorphic. Let's also go back to another important thing that we will notice. The conjugate of a theta n structure is a xi n structure, and the conjugate of a xi n structure is a theta n structure. Here again we see why these two structures are special. They are conjugates of one another. For example, the conjugate of 5 subscript 5 is 1 to the 5th subscript 5. Now let's notice a few interesting patterns in when we're doing conjugates before we go into the deeper meaning behind all this. Now let's say we have a sectoral structure, AN is equal to ABC and so on. We're not gonna, let's say it goes on to several parts. Then the conjugate of AN will be 1 to the power of n. And then remember, this wedge symbol means is continuous with 1 to the power of b is continuous with 1 to the power of c, and so on. Now keep in mind, when we're indicating this continuity, we're talking about the two adjacent sectors. So this can be further simplified to 1 to the power of a minus 1, comma, 2, comma, 1 to the power of b minus 2, because this will contribute on both sides, and this will be 1 to the power of c minus 2, and so on. But the continuity is that we're going to take the two adjacent sectors and turn them into their own part. So for example, let's look at 423 subscript 9. Let's write it out in this format here. So we will say the conjugate of an will be 1 to the fourth is continuous with 1 to the second, or 1 squared, is continuous with 1 cubed, is subscript 9. Now notice what happens here. This one is made up of two sectors, so it will contribute 1 to each of these continuities. This will contribute 1 sector, and this will contribute 1 sector. So what are we left with? We are left with 1 cubed, comma, 2, 2, 1 squared, subscript 9. So this is the conjugate of that one. And now if we do the reverse, if we take the conjugate of this, we go back to 423 subscript 9. So sometimes it helps out to write it in this format using the continuous with and alternating with symbols so that it makes more sense. Now let's take a few special cases when an is equal to a comma 1 subscript a plus 1. Its conjugate will be, we say 1 to the power of a continuous with 1, or 1 to the power of 1, and this will give us 1 to the power of a minus 1, comma, we get 1 sector from here, it becomes 2, and of course this has to stay the same, the n has to stay the same. Let's look at ab subscript a plus b. We say 1 to the a is continuous with 1 to the b is equal to 1 to the a minus 1, comma 2, so 1 sector from each, comma 1 to the b minus 1, and this has to stay the same. What about a 1 to the b, a plus b? So the conjugate here will be 1 to the a continuous with b. We take 1 sector from here, it becomes b plus 1, and this is 1 to the a minus 1. We add those up, it's still the same. This one is an interesting example. This is a1b. Here it becomes 1 to the a minus 1, and then it gets 1 sector from each side. This becomes a 3, and this becomes 1 to the b minus 1. Now notice there is a very important pattern that emerges. The number of beta joints in a sectoral structure and the order of the sectoral structure, meaning the number of parts, are related because we know that the order is equal to the number of beta joints plus 1. So let's say for a given sectoral structure, if it has an order of beta plus 1. Its conjugate, we will call the number of beta joints there beta bar plus 1. Now let's add those together. We get beta plus beta bar plus 2. Of course, what is beta bar? Beta bar is the conjugate of beta, which is alpha. So this gives us beta plus alpha plus 2. And we know that n, or the degree of a sectoral structure, is equal to beta plus alpha plus 1. So this equals n plus 1. So here we have an interesting rule that relates the order of a sectoral structure and the order of its conjugate using lambda for order. We say lambda plus lambda bar is equal to n plus 1. Okay? So this is very important to remember. Now in each sectoral set, in each complete sectoral set, STN, we have every sectoral structure must have a conjugate within that set. However, for some sectoral structures, not many, we've noticed that the sectoral structure itself is its own conjugate. So for example, we have this sectoral structure here. This is 1, 2, 3, this is 3, 1 squared 5. And it's got alpha, alpha, beta, beta. What happens if we take the conjugate? This becomes an alpha. So let's close it like that into an alpha. This also becomes an alpha. And then the two alphas become betas. So we end up with the same sectoral structure. So therefore, we say the conjugate of 3, 1 squared subscript 5 is also 3, 1 squared subscript 5. And for this reason, we call this sectoral structure a self-conjugate. And within certain sectoral sets of a given degree, there's a very interesting and useful pattern that emerges when we focus on these self-conjugates. So these self-conjugates form fixed points within these sets. So for example, let's look at ST3. ST3 is made up of 3 subscript 3, 1 cubed subscript 3, and 2 1 subscript 3. So the theta is the conjugate of the xi structure, and the xi is the conjugate of the theta. We are left with only one structure, and each structure must have one conjugate. So therefore, 2 1 subscript 3 is actually its own conjugate. Now we notice that when we have an even number of sectoral structures, or let's say even when n is an even number, then we notice that there is each sectoral structure has a unique conjugate, meaning there are no self-conjugates when we have even values for n. So ST4, ST6, ST8, they don't have any self-conjugate structures. However, for all the odd values of n, we notice that there are always, there's at least one self-conjugate. I will show you how we derive these very shortly, but what I want to show you is there is a way to figure out. Now we will call the set of self-conjugate sectoral structures of degree n, we will call that subset SGN, or self-conjugate n. And we will use these, of course, to indicate the size of the SGN. For example, for SG3, we only have one element in that set, which is 2, 1, 3. However, we notice that as the value or the odd value gets larger, the size of this self-conjugate set grows. And as we said, if it is even, the size is 0. However, when it's odd, there's a very clear way to calculate the size of that set, the self-conjugate set, and it is 2 to the power of n minus 3 over 2. So for example, and we will see shortly why that is. For example, if I have if I want to look at the self-conjugate set of degree 9, all I have to do is say 9 minus 3, that's 6, divided by 2, that's 3. 2 to the power of 3 is 8. So therefore, there will be 8 self-conjugates of degree 9. Notice that the order of the self-conjugate structures within a set is the same. And it will be as follows. It will be lambda, the order of that self-conjugate is equal to n plus 1 over 2. So when n is equal to 9, 9 plus 1 is 10, over 2 is 5. So it will have an order of 5. So therefore, if we want to look at all these self-conjugates of degree 9, we have to focus on the subset that has an order of 5. So we say that the self-conjugate set is a subset of the n lambda, of a specific n lambda subset. If we remember the n lambda subsets, those are the subsets of degree n and order lambda, where lambda is equal to n plus 1 over 2 in this case. We also notice another important property that we can correlate with, that at least one of the parts of a self-conjugate must be equal to 1. And this can be pretty easy to understand. The first joint of this structure, any sectoral structures, it is either going to be a beta or a 1. If it's a beta, then that last part, because we're going to go from largest to smallest when we write it, that last part of the sectoral structure must be a 1. However, if it's not a 1, if it's an alpha joint, then its conjugate must have a 1 here. That's just because either the structure or the conjugate must have a beta joint there. For this reason, in a self-conjugate, you will always have a 1 at the end of the structure. And the two examples we looked at so far confirm this, but we will see there are more examples. Because a self-conjugate structure must have at least one part equal to 1, therefore every self-conjugate sectoral structure must also be irreducible. So if you remember, we said the set of irreducible sectoral structures, we call that the characteristic set. So therefore, SGN is also a subset of the characteristic set of degree n. Now, if we look at the first few sizes of these sets, we will see the pattern starting with an n of, let's start with 1, 1, 0, because this is even, 2, 0, 4, 0, 8, 0, 16, 0. So this is the pattern that follows.